Hello everyone. Today, I would like to introduce you to our work Reparameterized Importance Sampling for Robust Variational Bayesian Neural Networks. Please allow me to first introduce the background of Bayesian Neural Networks (BNN). Bayesian Neural Network (BNN) is a probabilistic model that combines Bayesian inference with neural networks. They can perform probabilistic predictions by incorporating a prior distribution on the network weights and then inferring a posterior distribution using Bayes' rule. This characteristic empowers BNNs to estimate the level of uncertainty in their predictions, which is a crucial consideration, especially in safety-critical systems. However, due to the computational intractability of exact inference for posteriors, approximate methods are commonly employed in practice. Mean field variational inference (MFVI) stands out as a powerful paradigm for approximating the Bayesian posterior with flexible variational distributions. The optimization of this approximation revolves around minimizing the Kullback-Leibler-KL divergence between the variational distribution and the actual posterior. Unfortunately, despite the advantages related to computational tractability, training BNNs using MFVI can be challenging primarily due to the Monte Carlo sampling problem. Firstly, the majority of weights sampled from variational distributions tend to fall in edge regions, far from the most probable weight. Secondly, variational BNNs optimize variational parameters using stochastic gradient descent methods that rely on the gradient of the Monte Carlo estimate with respect to variational parameters. The Monte Carlo generating process of weights is the source of stochasticity in the gradient estimation process. High variance in the gradient estimators can impede or prevent the optimization process from progressing smoothly. These challenges become more pronounced when working with larger networks. Our work focuses on the sampling of variational distributions and the optimization of variational parameters. We consider the task of enhancing the robustness of BNNs by propagating the first moment during the feed-forward inference procedure. In a feed-forward BNN, the activation action of LTH layer can be expressed as this equation. The Monte Carlo sampling estimation of first-order moments can be expressed as the second equation. We investigate employing importance sampling for estimating the first moment as this equation. The importance sampling performs well when an optimal proposal distribution is used. A reasonable criterion for choosing a proposal distribution is to opt for one that minimizes the variance of first-order moments. We can obtain an optional optimal proposal distribution as the right equation by proving proposition 1. Unfortunately, calculating the optimal proposal distribution can be quite challenging, primarily because of the intractable integral involving nonlinear functions. In the following, our objective is to create a readily practical and highly accurate approximation for this optimal proposal distribution. Referring to the definitions of mean and variance, we can derive this. To simplify notation, we define all the nonlinear functions related to weights as HWL. We apply the Taylor expand and reparameterization trick to approximate expectations of HWL. Now that we have constructed an approximation of the optimal proposal distribution, however, we have observed that the likelihood gradients of variational parameters have a complex derivation. Therefore, we introduce a reparameterized importance sampling RIS method, which allows us to apply importance sampling in conjunction with the reparameterization trick. By specifying a particular distribution for epsilon, the weights sampled from the proposal distribution can be represented as a transformation of epsilon combined with the variational parameters. Algorithm 1 entails a detailed description of how the first moment propagates across each layer. Our experimental results demonstrate the effectiveness of the proposed RIS method in 3 critical aspects: improved convergence and enhanced predictive performance. Thanks for listening.